The two-way analysis of variance, or two-way ANOVA, as it's commonly abbreviated, is a more complex variation of the typical one-way ANOVA. It's far less commonly utilized as compared to the one-way ANOVA variant. However, from my experience, when it is utilized, it is often utilized completely incorrectly, or it is utilized correctly but with the results misinterpreted. In this lecture, we will discuss the two-way ANOVA at great length. If you haven't watched the prior video in the playlist, that being video number 31, which serves as an introduction to the topic of ANOVA, specifically the one-way ANOVA and Tukey's HSD post-hoc analysis, I would recommend doing so before viewing this lecture. As always, all lecture material, code, CSV, etc. can be found in the video description below. A two-way analysis of variance is a statistical test utilized to examine the influence of two different independent variables on a dependent variable. It also assesses whether there is an interaction between these two factors, is an extension of the one-way ANOVA, which involves just one factor. So factors are independent variables in the analysis. In a two-way ANOVA, there are two factors, factor 1 and factor 2. These factors can have multiple levels. Levels are the different categories of values for each factor. For example, if the first factor is treatment type with levels A and B, and the second factor is time with levels morning and evening, you have a 2x2 design. And what this means will become evident as we continue to go through the slides. Dependent variable is the continuous outcome you are measuring, and the interaction effect for a two-way ANOVA examines not only the individual effects of the two factors, but also whether there is an interaction between them. If the effect of one factor changes at different levels of the other factor, an interaction effect is present, and we'll also go over this as we continue on. Something I should also mention is the factors are the number of independent variables, and groups are the various categorical designations contained within each factor. So when will we use a two-way ANOVA? Well, when you want to analyze the effects of two different factors on the dependent variable simultaneously. Interaction effects, if you're interested in understanding how two factors interact with each other and influencing the outcome. And experiment design, commonly used in experiments where the researcher manipulates two independent variables. And those could be clinical trials with multiple treatment conditions over different periods of time. So here are a couple assumptions as it pertains to the two-way ANOVA model. The samples must be independent of one another. Normality, the data should be approximately normally distributed from each group. And homogeneity of variance, the variances within each group should be roughly equal. So we have a couple different hypotheses going on for our two-way ANOVA. Hypothesis 1, if you watched video 31 in the playlist, you're familiar with. It's the mean of one particular group is equal to the mean of the other equals to the mean of the other, depending on how many groups you have. Our second hypothesis is the mean of the second variable is equal to the mean of the first. And the third hypothesis is an interaction is absent or an interaction is present. So let's do a quick example. Here is our two-way ANOVA example. Researchers want to test the study habits within two schools as they pertain to student life satisfaction. In this case, the dependent variable is going to be stress. The researchers believe that the school that each group of students is attending may have an impact on study habits. Students from each school are assigned study material, which in sum totals to 1 hour, 2 hours, and 3 hours on a daily basis. Measured is the satisfaction of each student group on a scale from 1 to 10, after a 1 month duration. So our data set to the right is in the video description in CSV format. And here are our 3 corresponding hypotheses. For our first hypothesis, mean of 1 equals mean of 2 equals mean of 3, that is, stress levels do not differ depending on hours of daily study. And we have 1 hour, 2 hour, and 3 hour. Okay, so in this example, our factors are the independent variables, and those are study time and school. So study time and school are our factors, and 1 hour, 2 hour, and 3 hour, these are our levels within the factor study time. And as it relates to school, our levels are School A and School B. So for our first hypothesis, it's the mean of 1 equals the mean of 2 equals the mean of 3, because there are 3. This is for study time. The study time of 1 hour, 2 hours, and 3 hours, the mean. Stress measurements do not differ depending on hours of daily study. And the alternative is not all means are equal. Stress levels do differ depending on hours of daily study. For our second hypothesis, we're looking at schools. And it's mean of School A equals mean of School B. Here's school, here's School A, here's School B. Remember, this is a factor, school, and our levels are School A and School B. So in this case, the mean of the dependent variable stress, we're going to assume is equal both for School A and School B. So if we were to write this in plain terms, stress levels do not significantly differ depending on school. Our alternative is stress levels do significantly differ depending on school. And again, for this one, it's stress levels do not significantly differ depending on hours of study, 1 hour, 2 hour, 3 hour, and not all means are equal. Stress levels do differ depending on hours of study. And now we're interested in interaction. So the interaction is going to be present regardless as to how many factors and corresponding levels we have for our ANOVA. So we have, in this case, we have study time and we have school. So we have 2 factors, hence a 2-way ANOVA. However, we could have multiple factors. We could have study time, school, maybe gender, and then you might have an age category. And if that's the case, we wouldn't be limited to our 2 factors. So we wouldn't have a 2-factor ANOVA. In that case, we would have a multi-factor ANOVA. And we'd have a different hypothesis as it relates to each factor. And then this would be designated by the number of levels for each factor. Levels, again, for study time being 1 hour, 2 hour, 3 hour, school being School A and School B. Now, as far as interaction is concerned in our 2-way ANOVA, which again has 2 factors, if we have an interaction, and there only will be one interaction hypothesis for this particular 2-way ANOVA example, our null is the interaction is absent. The combination of school and study time is not impacting the outcome, and the alternative is an interaction is present. The combination of school and study time is impacting the outcome. And we'll talk about interaction in greater depth as we continue through this lecture. So if we wanted to perform this analysis, this 2-way ANOVA methodology of analysis in RCommander, we first have to make sure that this data has been successfully imported. We then would go to statistics, means, multi-way ANOVA, and this is in RCommander. Our factors are school and study time. These are our independent variables. And our dependent variable, our response variable, is satisfaction. I mentioned earlier that it was stress, but it's actually, I have it coded as satisfaction. So my mistake, our dependent variable is satisfaction. So we're trying to assess satisfaction as it relates to the variables school and study time. Here's what our output will resemble. So we have study time, school, and study time interaction with school. So this is the p-value for hypothesis 1, study time, our p-value for hypothesis 2, school, and our p-value for the interaction between study time and school. So we are going to reject the first null hypothesis. We're not and we'll be rejecting this on the premise that we have an alpha value of 0.05. So in this case, our p-value to two significant figures is 0.04, which is lower than our alpha value of 0.05. So we reject the null hypothesis, our null hypothesis as it relates to study time. We're not going to reject our null hypothesis as it relates to school because the p-value here is 0.58 and our alpha value is 0.05. So this value is, 0.57. This value is greater than our alpha value, so we do not reject the null hypothesis. And for our interaction, our p-value rounded to two significant figures is 0.63, which again is greater than our assumed alpha value of 0.05. So we reject the null hypothesis for study time, but not for school and not for the interaction. And I've highlighted degrees of freedom, the F values, and all of the P values because they're going to be necessary as it relates to reporting our findings in APA format. So here are our hypotheses. We reject the first, we fail to reject the second, fail to reject the third, which was the interaction. So we can state in plain terms, and then we'll do it in APA. There was a significant difference between the levels of study time as it pertains to stress, or as it was in our data set, satisfaction. So there was a significant difference between the levels of study time as it pertains to satisfaction. Students of different schools did not significantly exhibit different satisfaction levels. No interaction effect was present. And all that's stating is there was a significant difference as it relates to hypothesis 1, but not as it relates to hypothesis 2 or hypothesis 3. So we're reporting the results in APA format. This is what those results would resemble. Here are the degrees of freedom for the particular factor, and here are the residuals. Here's the degrees of freedom for this particular factor, school, and the residuals. And here are the degrees of freedom for the interaction and the residuals. These are the F level, the F value in each instance, and F value, F value, F value, and only one p-value is reported here because this value is less than our alpha value of 0.05, and so this was found to be significant. Not significant, greater than 0.05, not significant, greater than 0.05. So if we had results which resembled the following, we could do a post hoc analysis on the particular factor to try to determine where the differentiation exists as it relates to the levels of the factor. So in our example that we previously completed, our study time our study time independent variable was found to be significant. So we would run post hoc analysis on study time. Now, if school was also found to be significant, which it was not, I just changed the value, we would also could run a post hoc analysis on school as well. So we would run one on study time, one on school. Now, if either of these were found to be significant and our interaction effect was found to be significant, we would not run post hoc analysis on any of the variables. If you come to a situation where the interaction effect is found to be significant, you cannot run a post hoc analysis or interpret the results, regardless as to whether or not the results for either factor were significant as it relates to p-values. So we'll get into that in a moment. So here we're going to run a APA Tukey's post hoc analysis. Statistics, means, one-way ANOVA. We would select whatever variable is significant in our two-way model. In this case, it was study time. And our response variable is satisfaction. We're going to do a pairwise comparison of the means, and our confidence level is going to be 0.95 because our alpha value is 0.05. Here's our output. So we can see that the main differentiation as it relates to the levels within our factors was between 2 hours and 3 hours. And that is determined by the value here on the left and this value here on the right, which is our p-value. And as you can see, it's lower than our alpha value, which is 0.05. So we would need to report these results in APA format. We would also need to get the mean and standard deviation in order to do that. Now, if you need help reporting Tukey HSD outcomes in APA format, go ahead and watch lecture 31. That demonstrates how to do that. So you would need to report this as well as the mean and standard deviation for 2 hours and 3 hours as it relates to your data set. More information on that is in lecture 31. Now, if we find ourselves in a situation here, I just wanted to quickly demonstrate something because you might be a bit confused. If we were to run study time directly against stress or satisfaction as it is in our data set, in a one-way ANOVA, you'll see that the p-value is actually smaller than that of the two-way ANOVA. So this is study time with school and the interaction in the two-way ANOVA. This is our p-value and our residuals. And this, if we were to just run it one-to-one, with study time being our sole independent variable and stress or satisfaction being our dependent variable, the p-value is lower and the residuals are different. So you might be wondering, why is this as it is? Why is the p-value different? Well, I wondered the same thing, and when I was first learning this particular methodology. And the reason is that the degrees of freedom are higher in a one-way ANOVA as it relates to the residuals as compared to the two-way ANOVA with school included. So you have less unexplained variability, which means that the significance of each factor as far as p-value can appear stronger because you're accounting for more sources of variation in the model. And also, there's a reduction in error variance, and this is typically because a two-way ANOVA has more sources of variation to explain the overall variability of the data due to both factors and their interaction. So for this reason, residual error tends to be smaller. And with smaller error variance, the test statistic for each factor can become larger, which leads to a smaller p-value. All right, so now let's talk about what to do if the interaction was found to be statistically significant. What you're going to do is you're going to stop. So this is I played with these numbers here, obviously, as you can see. But if you do have a result which resembles this, where your interaction effect is found to be statistically significant, you cannot interpret any of the other variables within the system. So in this instance, our interaction is significant, but so is study time. You would not be able to then report the results of study time in APA format and state that a statistically significant finding was present, nor would you be able to run a post hoc analysis on this independent variable. You would just have to stop. You could not report your findings on study time or school. You could only report your findings in APA format as it pertains to the results of the interaction. And again, you're not going to be running APA on any of these if there is an interaction present. So this is how we would report this. If we find ourselves in a situation which an interaction was present, you can't properly interpret the main effects, those being the two independent variables, and you can only interpret the interaction. So the combination of variable A and variable B is impacting the outcome. And this would be reported in APA format as there was a statistically significant interaction or a statistically significant interaction effect of the school variable on the study time variable. And these will be your two independent variables in the two-way ANOVA. At the p less than 0.05 level, this would be your alpha value. This is your degrees of freedom for the interaction. This is your degrees of freedom for the residual, and this is your F value for the interaction in the output. And because our p-value is so low, it's less than 0.01, this is how the p-value would then be reported in the APA format. So this is how I typically remember an interaction effect in sort of regular, normal terms outside of, the statistical nomenclature. The gentleman on the left likes peanuts and he likes chocolate, but he does not like them together in peanut shoes. So an interaction effect occurs if one independent variable is impacting the other independent variable, and as a result of such, that interaction is impacting the dependent variable. So perhaps the amount of peanuts, the amount of chocolate, or some interaction between those two varying measurements, they're having an interaction on one another, which is impacting the outcome. And perhaps this will become more clear as we start to go through regression analysis in later lectures in this playlist. So if you run up against an interaction effect and an interaction effect is present, know that the impact of one independent variable on the dependent variable depends on the level of the other independent variable. And that is it for this particular lecture. All of the code and data sets as it relates to this lecture can be found in the video description below. I know that this was a long one, but it's a very complicated and nuanced subject, and I appreciate you staying to the end. Hopefully this was able to help you out with your research or your class or whatever it may be. So with that, if this did help you out, I encourage you to please like and subscribe. Hopefully we can get the YouTube algorithm to pick up on this so we can help other people out. And I look forward to seeing you in our next lecture. Take care and all the best of luck with your research.